Here is my explanation for one of the previous versions of the quiz. Of course, you can hit pause and rewind all you want. So I'm not going to just keep slowing down because you can have all the time you need. You can rerun it 10 times. So the first one, we've got our whole reaction laid out. Now, of course, on the left it says aqueous because we said in NIE. We're going to assume everything on the left is aqueous, so that's not even any help. We already knew that. And they even balanced it for us. This is supposed to be the layup one, the easy one. Now I get sodium nitrate and silver sulfide. And what are the states of matter for that? Well, if I look on my solubility chart, sodium and nitrate are both super solubles. So this is like extra double soluble. So that is very, very aqueous. Now, what about this? We usually look at the negative one. So let's find sulfide. That is here. It's usually insoluble or solid, not dissolved, and silver is not an exception to the rule. So silver sulfide would be a solid. So for net ionic equation, what we're talking about is let's not write down in our final answer the stuff that didn't do anything. So you probably need to take some notes for some of this. When a plus minus pair and ionic compound dissolves, we mean that they split apart. So the Ag went one way and the NO3 went another. And the same for the two sodiums. They went two directions, the sulfide went another, etc. So when this dissolved, when it's aqueous, it never came back from being dissolved. It's still dissolved. It did not form a solid and then dissolve. It stayed dissolved. And so these are not connected. This is not attached to that. You can mentally do this. It doesn't matter if we write it together, they're not actually connected. So the sodium was running around alone dissolved, two of them, and the same is happening here. And the same for the nitrate. There are two of them running around dissolved, and they were dissolved running around alone, two of them previously. So nothing happened to those two. So let's do this. I mean, you don't have to for the answer, but it might help you to remember what we're doing if you scratch out the things that are the spectator ions. They just watch what's happening. They didn't participate. So if we scratch those out, what we're going to get is the net ionic equation, what really happened. And remember, net is the opposite of gross here. And I don't know why it's called gross, but gross is the overall picture, like your income before taxes, and net is after you do all the accounting, what really, really happened that counts. So what happened that counts is there were two silver pluses, and you know they're plus because you looked at your ion chart here. Silver is +1. There were two of them, and they were aqueous, and they met up with an S minus 2 because you looked at your periodic table and S is minus 2, and it was aqueous, and they made this solid, and that's your net ionic equation. On this one, we know the iron is +2. We look up nitrate, it's -1, so there must be two of them. We know that everything on the left is aqueous. Cesium is a +1. Look at my periodic table. Hydroxide is OH -1, and it's on this solubility chart. So the charges had to add to 0, but they already do. We know everything on the left side is aqueous. Now let's trade the partners. The cesium will go with the other negative, so +1 -1, and that works. And the iron is +2, and it goes with this -1. Remember, +2 -1 if you like. So that means there must be two of those. Then the thing I usually forget to do is balance it left and right. So the two hydroxides here, put a 2 here, and that makes two cesiums, so I put a 2 here, and that makes two nitrates, but I already had two nitrates, so I solved that sort of by accident, which is a very good sign for me. So remember we said nitrate is a super soluble, so this is going to be aqueous. The other thing to check, though, is hydroxides. So we grab our solubility chart, and hydroxides are here, and they tend to be insoluble. And is iron 2 an exception? No, it's not. So that will be insoluble. It will not dissolve. It will be a solid. And by all the same reasoning as before, we have two of them that formed a solid and two that stayed aqueous. So the two that stayed aqueous didn't really do anything, so we could do that. And what we had was we had one of these +2 that was aqueous met up with two of those OH minuses that were aqueous, and they made this solid. Here we have an acid-base reaction. We didn't really talk about it in those terms, but just so you've heard it, because we said acids are things that give off H plus. Some of you might sort of remember that that's phosphoric acid. And bases are things that take H plus, but OH minus is a thing that loves to take H plus, because if you take an H off of here and put it on one of those, you get water. You have two H's and an O, and that's water. So if we take our plus here, our plus ion, and made it up with our minus ion here, we get water. And or you could write it HOH if you really, really want. And we take our plus here and made it up with the minus here, we get this, because this is a +2, look at your periodic table. This is a -3, look at your ion chart. And this is our classic 2-3 problem. So we need 2 of these and 3 of those, so that I have 3 sets of +2 is +6, 2 sets of -3 is -6, and now the charges add to 0. Now, another very common mistake is that kids will put water is aqueous. Well, it's in water, yeah, but it's not dissolved in water. It is water. So that's a small capital L for liquid. I don't think I've ever seen anybody put a capital L. Could you not do that? They might actually mark you off a little bit in a college class. I've never seen anybody do that. Capital L is liters, and here that wouldn't make any sense. Now, what about phosphate ionic compounds? Phosphate is, here it is. They are generally insoluble solids and is our calcium an exception to the rule? No, it is not. So this will be a solid, and it's, in this case, everything changed. So I kind of ran myself out of room, but we're going to separate these, and we're going to put the charges on everything. There were 3 Ca plus 2s, aqueous. There were, remember this is 6, 3 sets of 2 sets. There are 6 OH minuses that were aqueous, and also on the left there were 6, 2 times 3, H pluses that were aqueous, and 2 phosphate groups that were -3 that were aqueous, and they made that. And I didn't feel like writing it out, but we can maybe, just to save time, we can do that there. On this one, we trade the partners, and we get the ammonium with the chlorate. And that's +1, -1, because I looked at my ion chart. And then I get my beryllium with my bromide, and that's a +2 -1, because I looked at my periodic table. So the charges had to add to 0, so there must be 2 of these here. Now we balance everything left and right. And let's see, 2 Brs makes me put a 2 here, but that makes 2 ammoniums, which puts a 2 there. But that makes 2 chlorates, but I already need 2 chlorates, so that works out great for me. Now remember, we said, no, we didn't say yet in this one, did we? Ammonium is a supersoluble, which you know from there. Ammonium is going to dissolve very, very well. So this is going to be an aqueous for sure. The one that I didn't actually personally remember is this one. I had to go look it up for real. And we look up the negative one. That's easier. These are pretty much keyed to the negatives mostly. So where's my Br? There it is. And what did we have with it? Beryllium. So is beryllium an exception to Br liking to dissolve? No, it's not. So this Br compound with beryllium, because it's not there, will be soluble. It will dissolve. So this is aqueous too. So everything was aqueous dissolved running around separately. No matter how many times you write it together, it's not actually together. And the same thing is happening over here. Just because you rearrange them and write them down doesn't make them actually stick in real life. You know, it's like saying I am 7 feet tall. It doesn't make it true. You can write it all you want. And just because we put these together here doesn't actually make them true. We double check with reality, which is what we're doing when we look at the chart. And it turns out both these would dissolve, and we know both of these would dissolve, or at least the versions we were working with would dissolve. And we're working with the little bits that would dissolve or something. And so everything crosses out, if you want to look at it that way. And so there is no reaction. Nothing really changed.